We have already discussed one of the most important results in functional analysis, the Banach theorem. Today we will discuss two more very important results. One of them is the open mapping theorem, and the other one is the inverse mapping. We will start with the open mapping theorem. Let me start with the definition of the open mapping. It is fairly simple. We call a mapping open if it maps open sets to open sets. And I will state this definition in general metric spaces. So we take two metric spaces and a map A from X to, or rather let's go for the map phi. Let phi be a mapping from X to Y. A mapping is called open. If A of U is phi, phi of U is open for every open in Y, for every open set U from X. And let me now state the open mapping theorem. From X to Y. And we further suppose that this mapping is surjective. Then this operator is open. So the proof of this result is fairly long, and we will spend most of this lecture to prove this result. And the proof of the theorem based on a very interesting observation due to Stefan Banach. This observation by Banach doesn't look very intuitive, well, at a glance. Well, at the second glance, it doesn't look any more intuitive. But let me state it anyway. So let us take two Banach spaces and a bounded linear operator, which is surjective. Then there exists a positive number R such that the ball in Y, since we have two spaces, we have balls in both of them, so I will, by the subscript, I will specify in which space we consider this ball. So the ball in Y centered at 0 and of radius r belongs to the image of the unit ball from X. So what does it mean in words? It means that if we consider a unit ball centered at 0 in X, then the image of this unit ball under the mapping A contains some open ball. So let us prove this. First of all, let me write the space X as a union of balls of increasing radius. Balls in X centered at 0 and of radius n. Next, let us take an arbitrary element from Y for any point. Since the mapping A is surjective, so it's onto this space, this Y equals to some A of X for some X from X. Let me write it in words. Since A is surjective, there exists X from X such that Y equals to A of X. Since the space X is written as a union of these balls, then this X does necessarily belong to some of these balls. There exists, say, n0 such that this X belongs to the ball centered at 0 and of radius n0. Which means that Y belongs to the image of this ball. And we can conclude that the whole space Y can be written as a union of such sets. Hence, Y equals to the union of balls. Well, clearly the same result is true if I will take the closure of these sets. We have written the space Y as a union of infinitely many closed sets. And we know that Y is a Banach space. So by the bare category theorem, at least one of these sets contains an open ball. There is at least one set that contains an open ball. So this set is the closure of the image of a ball. If I shrink this ball, so this ball is of radius n, I want to consider the ball of the radius 1. So if I shrink this ball, then using linearity of A, I can conclude that that smaller set also contains an open ball. So I take the image of the unit ball and take its closure. Let's call this ball, so it's a ball in the space Y, and let's say it's centered at Y0 and of radius delta. Before we go any further, I will state a couple of properties of these sets, the closure of the image. So the first property which I want to prove is that a point Y belongs to this set if and only if the point minus Y belongs to this set. Well, by the definition of closure, the fact that Y belongs to this closure means that there exists a sequence of the elements which converge into this point Y. So let us take Y from this set. Then there exists a sequence Yn from the image itself, such that this Yn converges to Y. Since the operator is surjective, then for each Yn we can find Xn from X such that Yn equals to A of Xn. But then the sequence of minus Xn's is still in the unit ball, and A of minus Xn converges to minus Y. Or rather, minus Yn equals to A of minus Xn converges to minus Y, which means that minus Y belongs to the closure of this set. The second property of this set which we need is that this set is convex. So let us take 2 points from this set and some scalar between 0 and 1. And take lambda between 0 and 1. Well, by definition, these 2 points belong to the closure, so we can find two sequences which converge to Y and Z. Two sequences converging to Y and Z respectively. Again, using the fact that the operator A is surjective, we can find the sequences from the unit ball say xn and tn such that yn equals to a of xn and zn equals to a of tn. Well, these sequences, both of these sequences are in the unit ball in X. But since the unit ball is a convex set, we have that the sequence lambda xn plus 1 minus lambda tn belongs to the unit ball. Now, using the linearity of A, we obtain that lambda y plus 1 minus lambda z belongs to the set, to the closure of the image, which means that this set is convex. Having these two properties, let's go back to the fact that this set contains an open ball centered at y0. So let us take a point y back to proof. From the ball centered at 0 and of radius delta. So over there we deduce that the closure of the image contains a ball which is of radius delta and which is centered at y0. Now I will show that this set contains the ball of the same size but centered at 0. We have that the distance from y0 to y0 plus minus y equals to, well, in particularly y is a Banach space, so it's a normed linear space. So its matrix comes from the norm. So to find the distance between two, we find the norm of a difference. Yeah, but writing plus minus over here, in one go I consider two elements, y0 plus y and y0 minus y. For any of these two elements, over here in the norm, we have just the norm of y. But y belongs to this ball. So the norm of y is less than delta. So the distance between y0, which is the center of that ball, and this point is less than delta. So these 2 points belongs to that ball. But this ball is contained in the closure of the image. Hence, both of these points belongs to the closure of the image of the unit ball. And since we have proved that a point belongs to this set if and only if minus 1 times this point belongs to this set. So I conclude that the points y plus minus y naught belongs to this set. In particular, well, not in particular, so having this, we will use now the convexity of this set to show that the point y belongs to this set. The point y can be written as 1/2 of y plus y naught plus y minus y naught. And since this set is convex, then this point belongs to this set. We have proved that this ball of radius delta centered at 0 belongs to this set. Well, no belongs sits inside. It's a subset. So the closure of the image contains some open ball. But in the statement, what we want to prove is that not the closure, but the set itself contains an open ball. That will be the second part of this proof. Having this conclusion, what we can do, we can take an arbitrary constant So if I enlarge the ball on the left c times, then I will get just the ball of the radius c times delta. And if I enlarge the set on the right by c times, using the linearity of A, this will be the image of the ball of the radius c. Now let me take a point y from the ball of the radius delta centered at 0. Using this inclusion, I can find x1 from x such that it belongs to the unit ball, so the norm of x1 is less than 1, and since this ball belongs to this set, y minus x a x1 is less than delta over 2. Further, using this inequality of this, using this inclusion with constant being 1/2, we can find x2 from x such that, so c is 1/2, so this x2 belongs to the ball, belongs to the ball of radius 1/2, and combining this one, y minus ax1 minus ax2 is less than delta over 4. And so on. We can continue this. So we can find xm from x such that the norm of xm is strictly less than 1 over 2 to the power of m minus 1. And the norm of y minus the sum of axi is less than or equal to delta over 2 to the power of m. Note that due to the choice of the norms of xm, we can conclude that the series, the numerical series, strictly less than 1 over 2 to the power I minus 1, well, which is less than infinity. But we know that if the series of norms converges, then the series of elements converges as well. So we conclude that the series of elements xi converges in x. But we have assumed that X is a Banach space, so this series converges to an element of X. We can also estimate the norm of X. Using the triangle inequality, I can estimate it by the sum of norms. But we have seen this already, so this is estimated from above by this sum. Which is 1 plus half plus quarter plus 1 over 8 and so on. So this series equals to 2. So the norm of x, which we constructed, is less than 2. Now let us take this estimate from the construction of xm and take the limit when m tends to infinity. We have that y minus a of x equals to the limit when m tends to infinity, y minus the sum of axi, but this was estimated by delta over 2 to the power of m. Which is 0. So y equals to a of x. What did we do? We've taken y from this ball and found x from, well, with the norm less than 2, such that y equals to a of x. So we have proved that that ball of radius delta is a subset of the image of the ball of the radius 2. So the normal fax is less than 2. To prove the theorem, we just take R to be delta over 2. And we're done. So the image of the unit ball of a surjective mapping contains a ball.
Let us now prove the open mapping theorem. Let us take an open set U from X, and we want to prove that the image of this set U is open as well. So by definition of the open set, we will take a point from the set A of U and show that it belongs to A of U together with some ball around it. Since Y belongs to the image, there exists X from U such that A of X equals to Y. And since U is open, then X belongs to U together with some neighborhood. From the previous theorem, we know that the image of the unit ball in X contains some open ball. Let us now consider the open ball in Y centered at the point Y and of radius R times delta. Making this shift, we can write it as a ball centered at 0 of the same radius plus Y. And now we can factor this delta out. But this ball is a subset of this image. So we have since A is a linear operator, we can bring this delta inside. And since y equals to a of x, well, we can write it as a of x. Further, using the linearity of a, we can write it as this one. And further, but this ball belongs to u. So the image of this ball is then is a subset of a of u. So we proved that the point y not just belongs to a of y, but it belongs to a of y together with some ball around it, which means that a of y is open. And we're done.
Let us now state the result, state and prove the result, which is called the inverse mapping theorem. So let us take two Banach spaces and a bounded linear operator between two of them, and also suppose that this operator is bijective. If A is bijective, then its inverse is a bounded linear operator as well. So let me first note that the existence of this inverse operator follows directly from the bijection. So it's a one-to-one mapping. So for any point in y, there is a unique point in x such that y equals to a of x. So the inverse is always defined. So what we need to prove is that the inverse is a bounded operator. Linearity again follows directly from linearity of a. And here we will use the Banach theorem which we have proved. A is bijective, which in particular means that it is surjective, so we can apply that theorem. By Banach theorem, the image of the unit ball contains some ball. Now, let me take a point y let's take this y of norm r over 2 for this r. So if the norm of y equals to r over 2, then it belongs to this ball of radius r. And in particular, this y belongs to the image of the unit ball. Which means that there exists x from the unit ball such that y equals to a of x. And let us note that since x is from the unit ball, its norm strictly less than 1. And 1 equals to 2 over r times the norm of y, which is equals to r over 2. So it's nothing but 1. So since A is linear, well, in particular homogeneous, then for every y from y without the restriction on the norm, there exists x from x such that the norm of x is less than 2 over r times the norm of y, and a of x equals to y. But since A is a bijection, this equation has the unique solution. Then x equals to y inverse, A inverse of y. And so if we substitute this expression for x into that last inequality, we get that the norm of A inverse of y less than or equal to 2, strictly less than 2 over r times the norm of y, which means that A inverse is a bounded operator. And we're done. These results have very interesting corollaries. So let me state some of the corollaries. Some of them will be exercises for you, and well, some of them will be proven. Let us consider a non-linear space with two norms on it. And such that there are two norms and x is complete with respect to both of them. Let us suppose that, say, this norm is less than or equal to the other norm up to a constant. For every x from x. And it turns out that this inequality is enough to deduce that the norms are equivalent. That will be an exercise for you to prove. Let me state one more result which provides us with the criterion of invertibility of an operator. Okay, let us take two Banach spaces and an operator between them. And the following two assertions are equivalent. The first statement, the operator A is invertible. And the second, the image of A equals to Y, well, which means that the operator is onto, and there exists constant alpha such that the norm of AX greater than or equal to alpha times the norm of X for every X from X. So from 1 to 2 is simple, and it will be an exercise for you. As a hint, take alpha to be 1 over the norm of A inverse. I will prove the implication from 2 to 1. Let us suppose that the image of A is Y, which means in particular that A is surjective. And from the inverse mapping theorem, we know that if the mapping is bijective, then it is invertible. So what we need to prove is that it is injective. Well, yeah, injective, which means that A of X does not equal to, A of X equals to A of Y if and only if X equals to Y. Or equivalently, the injectivity means that the kernel of A consists of 0 only. So let us take an element from the kernel of A. Well, which means that since it's from the kernel, it means that A of X is 0. Or in particular, the norm of A of X is 0. But the norm of A of X can be estimated from below by alpha times the norm of X, which is also greater than or equal to 0, which means that the norm of X is 0. And X is 0. So we've taken an arbitrary element from the kernel and prove that it is 0. So the kernel of A consists of 0 only, and hence A is injective. Combining this with surjectivity, we deduce that A is bijective and therefore invertible. In the previous lecture, we considered the multiplication operators. For some F, for some fixed element from this space. Well, yeah. Just specified the domain and codomain and forgot to write the formula. So mf of u equals to f times u, or rather, t. And we have seen that for f equals to t plus 1, this operator mf is invertible, its inverse is a multiplication operator, multiplication by the function which is 1 over f. So we have seen that before. And also, we have considered another multiplication operator, f of t equals to t. And we discussed that we cannot write down the inverse of this operator as we did for that one. Well, there is a reason, because we cannot divide by 0. Having proved this result, we can deduce that this multiplication operator is not invertible. Indeed, if we consider the image of this operator, if we take any function v from the image of mf, then, by definition, this v equals to f times u for some function u. But f equals to 0 at 0. So in particular, this v also equals to 0 at 0. V of 0 is 0. So any element from the image of this multiplication operator equals to 0 at 0, which means that the image does not coincide with the whole space. And so by the theorem, we conclude that mf is not invertible. We have the only one topic to discuss, and this topic is the closed graph theorem. Before we define the notion of the graph, well, and of the closed graph, let me recall how we define the norm on a Cartesian product. So let x and y be two normed linear spaces. Well, define a Cartesian product of x and y as the set of all pairs of elements where the first element is taken from x and the second one from y. Using that norms on x and y, we can define the norm on the Cartesian product. So we take a pair of elements, and the norm of them is defined as a sum of the norm of x and the norm of y. The norm of x in x plus the norm of y in y. It's fairly straightforward to verify that this is in fact a norm. What is more interesting, but again not very surprising, is that if both x and y are Banach spaces, then the Cartesian product is Banach as well. So further, let me define the notion of a graph of an operator. Let A be a linear operator from x to y. Let me define the graph of A as a subset of the Cartesian product of x and y. We will denote the graph of A as G of A, and it consists of all pairs of the form xa of x from the Cartesian product. From the linearity of x and A, it follows that G, the graph, is a linear subspace. It's a linear subset. And let us call an operator closed if its graph is a closed set. Let me state an if and only if condition for an operator to be closed. So let A be a linear operator between two non-linear spaces. Then A is closed if and only if xn converges to x, well, in x and A of xn converges to y in y. So if these two conditions imply that x belongs to x and A of x equals to y. And also belong to y. So this is, the proof of this result is just a consequence of the definition of being closed for the graph. So I leave it for you as an exercise. At this point, you might ask me, why did I introduce a new notion, although this one looks like continuity? And indeed, if an operator is continuous or bounded, which is the same thing, then it is automatically closed. But the converse is not necessarily true. But if we are in Banach spaces, then these two notions are equivalent, and this is in fact the closed graph theorem. So let me note over here that any bounded or, well, continuous operator is closed. And let me state the closed graph theorem. Let x and y be Banach spaces, and let A be a closed linear operator from x to y. Then this operator A is bounded. Let us consider the graph of this operator. Well, since A is linear, well, and x is linear as well, the graph is a linear subset of x. Also, since A is closed, then G of A is closed. So it's a closed linear subspace of a Banach space, which means that it is a Banach space itself. closed linear subset of the Cartesian product of x and y. And since both x and y are Banach spaces, then so is its Cartesian product. Hence, this graph of A is a Banach space as well. Let us now define an operator from the graph G of A to x, which will be a projection onto the first coordinate, onto x. So define a projection from the graph onto x. By saying, well, the elements of the graph are pairs, x and a of x. And the projection acting on this pair just returns x. First of all, this projection operator P is linear. Further, let's prove that P is bounded. Let us consider the norm of P of x, A of x, which is by definition of P is nothing but the norm of x in x. Now, I estimate it from above by adding the norm of ax but this is the norm in the Cartesian product of the pair x, A of x. This norm is in x, the first one. And this, the last one, is the norm in the Cartesian product. Well, which tells us that this operator P is bounded. I want to prove that this operator P is a bijection for every x we have that P of xax equals to x by definition, which means that this projection is surjective, so it's onto x. Let us now prove that it is injective, or in particular the kernel consists of 0 only. So let us take an element from the kernel . By definition of the kernel, the value of P at this point is 0. But by the definition of P, it equals to the first component, so x. So x is 0. But the operator A is linear, so A of x is 0 as well. So we've taken an arbitrary point from the kernel and proved that the first and the second components are zero. So this point is zero in the Cartesian product. Equals to zero. This is slightly larger. Zero, it is zero of the Cartesian product. And so P is injective. And taking this all together, P is bijective. So we have a bounded linear operator from one Banach space to another Banach space, which is a bijection. By the inverse mapping theorem, it is invertible and its inverse also a bounded linear operator. Yeah, and well, P inverse is of course an operator from X to G of A. And also note that P inverse of X equals to X AX, the pair for every X from X. Then we have that the norm of AX in Y is less than or equal to the norm of X in X plus the norm of AX in Y, which is nothing but the norm of a pair X AX which is, by definition of P inverse, is the norm of P inverse of X. But P inverse is a bounded linear operator. So this is less than or equal to the norm of P inverse times the norm of X. Well, in X, of course. Which means that A is bounded or continuous because these two properties are equivalent. The operator A is bounded, or well, continuous. And we're done. Let us finish this lecture, or rather this course, with the example of a closed operator which is not bounded. In this course, we haven't seen many unbounded operators. We mostly dealt with bounded linear operators, but there was one operator which we proved is unbounded. It was a differentiation operator. So let us consider an operator D from the space of once differentiable functions on the interval 0, 1 into the space of just continuous functions on 0, 1. Both of these spaces are equipped with the uniform norm. And D is nothing but the differentiation operator. So it takes a function f and returns its derivative. Well, we have discussed that this operator is unbounded. prove that it is unbounded. So we just need to take D at xn where, let's go with f, where fn of t is t to the power of n. The norm of each of these functions is 1 on the interval 0, 1, but the norm of dfn, when you differentiate it, you will get n in front of it, and so it will be unbounded. Let us now prove that this operator is closed. So we have stated the criterion for the closedness of the operator. So let us take a sequence of functions from the domain. Let's take this sequence of functions from the domain such that this sequence itself converges to some function f in the uniform norm, and the sequence of derivatives of fn also converges to some other function, again in the uniform norm, to 0, of course, 0, 0. Hence, fn of t minus fn of 0. This is what we have. So I'm just using the fundamental theorem of calculus. These converges uniformly to the integral of g of s ds. On the other hand, the left-hand side converges to f of t minus f of 0. Combining these together, we get that f of t equals to f of 0 minus plus the integral from 0 to t g of s ds, which means that g equals to f prime. And so the graph of this operator D is closed. Yeah, I have no room to write it down.